Okay, so we will start off with the very basic grouping, the user-defined group parameter. So we start off by coming out of the input mesh, in this case the rubber toy again, and that feeds into group create, input user group, and we just pretty much expose all the parameters except the only visible parameter is the base group parameter, and this is where the drop-down menu is in the HDA. So if we head on up to the HDA, if we turn off use bounding object, and this is where it is exposed, the base group parameter. And if you are wondering where the other parameters are exposed at, they are not. The user doesn't really need to establish the rest of this. The reason that it is exposed in the HDA and is invisible is if we go into the type properties to pull up the HDA file. They're not visible right now, but if we show invisible parameters, you'll see them appear. The reason for that is, and a lot of people have trouble with this when they're making their own HDAs, whenever you try to expose the base group parameter to an HDA, a lot of people will get hiccups, including myself, because it won't work. It'll give you an error message. The reason for that is the base group parameter requires all of these parameters in this node to be exposed at the HDA level. It cannot read it from the node level, so it needs to be in the same directory, if you will. So whenever you are trying to expose a base group parameter of your own, you have to unfortunately put everything else within the HDA. And if you do not need them, you just make them invisible. As you can see right here, there's a checkbox, invisible. And you can just turn this on and off to show the invisible parameters. Hit that. So I just wanted to go over that because that is a common issue that I encountered before, and that frustrated me. So yeah, so whenever you expose a base group parameter, if it gives you an error message, it just needs the other parameters within the HDA. All right, and what we do now is whatever the user inputs as the primitives to use as the circle, we are naming that group circle points prim. Okay, so coming out of the input group down below, we move on down to group promote circle points prim. If we highlight this right there, that is pretty much promoting the primitive selected to make the circle, and we're going to put that into a points group. And we will be using this group later on to drive the circle math, but more on that later. Anyway, that finally feeds into right down below the use bounding box as opposed to manually selecting the group, as I explained before. This is the parameter that is exposed in the HDA right here, and we could turn that on because we are going to cover the bounding object groups next, which is the scary part. So we dig back in here and we go all the way up, and now we get to work on the right side of the grouping graph, the use bounding box option. All right, so what we do is we feed our input mesh, once again, the rubber toy in this case, that feeds into a group node. And right here, the second input, you may have seen this before if you are familiar with the group node. The second input is for a bounding box object. So that is represented once again by this input right here. And if we go up into our graph, that is what is being fed into the second input of the Circle Topo bool. Back inside, and we notice our group. We are creating the circle points as defined right here. And you'll see those points highlighted, and you'll see some funkiness right there, which we will take care of within the edge detection graph right here, but we'll get to that later. Anyway, this group, we are making these circle points based on what is inside of this bounding box. So if you're making this from scratch at home, you are going to have keep in bounding regions enabled, bounding object points or vertices only. And so that's why we are holding off on the circle points prim option, because this only takes points. So we will cover the primitives group later. If you remember, the first option, the user defined option that made the group circle points prims, the primitives group, that made that first, but we have to hold off on that because, again, the bounding box object only takes points. So that is the reason for that. Don't worry, the circle points prim group is coming. Anyway, this group node, to make things simple, we'll cover this last, but we come out of this group node and we go all the way down. Group promote, circle points prim. This is where we make our primitives group for not using edge loop detection. So this is what happens if we go up in our graph. This is what happens. This is what we get if we turn this off. And that is being fed into right here, the switch node. And so the switch node right down below is exposed right here. Use loop detection. So that's what's being fed into there. All right. And so this is what you get if you turn that option off. Circle points gets promoted to circle points prim, as you see in the graph. And again, you want to keep original group, absolutely keep that on, and include only elements contained entirely within the previous group, or else that'll happen and that'll distort your selection. So you want to keep this checked, and you can see how funky that geometry is. It's going to make a very funky looking circle, so that is why I've included the option to use loop detection. So a very handy feature to have, and we will cover how to group that next. Oh my, look at that graph. So right here we are splitting off the chosen geometry from the actual mesh. If we highlight this node right here, the delete node, we are isolating that temporarily and we will reassemble it later. But right here the geometry is full and feeds back down into this bottom node right here, attribute wrangle 6. And we have some vex code here to pretty much get the groups and reassign everything to the original geometry. I deleted it originally just to make life simpler. We're going to use the deleted unshared edges as a way to determine if there is a proper edge loop within this group to make a circle, and pretty much we're going to shave this down procedurally with Vex Magic, which would be much harder otherwise if this geometry were intact. So you'll see right there, circle points prim, that is the final product. That is the perfect square that will create our circle. So we have to determine this group based on the bounding box object from the circle points group. Hopefully I didn't confuse you, but down below here, we pretty much delete the original circle points group because that was all funky, as we've seen, because it's based on a bounding box, and then we recreate that group based off of the result from this graph right here that determines our edge loop. So hopefully I did not lose you, but let's dig inside the graph one by one. So the group circle points node, the original group node that's being fed directly from the inputs as I shown before, we are going to branch out of that to an attribute wrangle 3 node. If you have seen my previous tutorial, Make Circle Great Again, we are doing the same thing where we are assigning an ID attribute to the points and assigning the point numbers to that ID attribute. And this way we can identify which points belong where after we have deleted the geometry, because as you know, once you delete geometry, the point numbers get recalculated from scratch. So we are using the ID attribute once again to get the original point number so we retain that information. All right, so this is just to retain our original point number so we can reassemble everything properly later on and pass on some attributes. Beneath that, we have another attribute wrangle, and this is for primitives, and we are doing the same thing for the primitives. I at primid, you can make up whatever name you want, equals at primnum, and this way we can identify the same exact primitives, because once again, once we delete everything, the primitive numbers will get reassigned a new value compared to the original geometry, and you'll see those numbers just changed. So most of you are familiar with this concept, so I won't bore you. All right, and once again, this attribute wrangle right here, this feeds into all the way at the bottom, attribute wrangle 6, where we reassemble everything. And also from this, we will branch out into the main scary portion of the graph down below, this long chain. This also feeds out into our delete node, where we delete non-selected circle points. So this feeds into this node right here, remove try trash. This is a primitive wrangle that I've made. This is probably not necessary, but I like putting it in as a safety. It just pretty much, when you delete points, you'll see that it leaves some triangles because some of the points you selected, it's not selecting primitives. Again, we had to select points because the bounding box requires it, so we have to do some rigmaroling to get around the point selection. But you know, once you select points and delete them, you'll see that there's some triangles right here. Remove try trash, gets rid of them. It is a primitive wrangle and it goes through each primitive. So it'll go through each and every one of these things, and if it only has 3 or less points on it, we delete it. So that's pretty much what remove try trash does. The vex code below is int point count, and it's an array. So that will equal the vex phrase prim points, parentheses 0 at primnum. And what prim points does, it makes an array, so we have to declare it an array, and it returns the points that are contained in each primitive. And we are making an array with that called ptct point count. And luckily, even though it's an array, we do not have to do anything going over each of the indexes. So we just need to measure the length of this array. So that is what this is down below. Int length equals len, another vex phrase, parentheses ptct. And what this does, it returns the length of an array, as you see from the help menu. And pretty much if this equals 3 or less, we are going to remove this primitive down below. All right, and this if statement, it just sees if it has less than 4 points. And if it does, we are going to remove that primitive. As you've seen, they've already disappeared. And what you want to do is remove prim, parentheses 0 for the geometry input number. So that's coming into the first input, which is input 0, at primnum. And this is where some people may get confused, comma 1. You need to put that in this case, because what 1 means is it'll delete the points as well. If you do not have the 1 there, it'll delete the primitive, so there's faces missing, but the points will remain. I'll show you what I mean. So if we highlight our points, you'll see that we have floating points. It kept the points. You need to set this to 1 if you want to have the points gone as well, which we do. And you see they just disappeared when I reset this back to 1. All right, so beneath the remove try trash node, we are going to yet again an attribute wrangle. And what we're doing here is getting a center point, and we are measuring the distance each point has from that center. So what it's going to do is pretty much just get, what is a central point based off the bounding box of all these points, and measure each point's distance from it. And the reason we are going to do that is we need to sort these points down below right here by the distance from the center at, in this case, the descent attribute, which we set up right here. I'll go over this in a minute, but we're going to sort that from smallest distance to largest distance, and then that'll feed into this attribute wrangle right here. And we're going to set the sort node into the second input of this attribute wrangle right here. First input gets this attribute wrangle, the main geometry that'll be, of course, fed into the first input. And it's going to take the very first point from the sort node going into the second input. It's going to return the first point, and that first point is obviously going to be the point that is closest to the center. And we are going to fetch its ID value. All right, and what this vex code down below does, I'll go over this more in detail. This is going to remove all the points that are not that center point from the group circle points. So we will only have 1 point left in our circle points group temporarily. We will reset it later on, and that point will be our center point. That'll be where our circle will start at the center. So once again, right here, we are going to find the center point. And this is how you get the center point. Vector center equals get bbox underscore center 0 for the first geometry input. This pretty much makes an x, y, z vector with the locations of the center point of the bounding box. It does not return an actual point's position. It is just putting a box around this like a bounding box and then finding the center location of that. We are trying to find the distance each point has to that position. Down below, with this value, the float at distcent, so distance center, I just shortened it to distcent, equals distance, and we are measuring the position of each point, this is a point wrangle, to the center. If we go into our geometry spreadsheet, you'll see that right here we have the distcent for each point, and we are going to sort these with a sort node, so it goes from shortest distance to the highest distance. So you just plug this into a sort node, sort by attribute, descent, and the component, if you do not know, that's not necessary because this is a float value. Components are mainly for vector values. If you want to isolate the vector of the x is 0, y is 1, 2 is the z value. But yeah, so that's what the component is. You do not need to worry about that if you're just using floats and integers. And again, attribute wrangle 2 down below. You feed in your main geometry into the first input. The sort goes into the second input. And this short bit of x goes into a point wrangle. So int selected equals 0.1 for input number 2. So it's getting input number 1. This is 0. This is input 1. It is trying to get the first point, the sorted input where we sort from shortest distance to the center to the longest. And it's going to return the original point number, which is the ID value right here. All right, and this is coming from the second input, and so we're going to match that to the first input's geometry to rearrange our group. So if the ID attributes coming in from the first input do not match this point right here, we're going to remove them from the group circle points temporarily. Again, we'll reset the group circle points later on. So the syntax for grouping points is set point group, parentheses, 0 for the first input we are working on, the group name in a string, circle points, comma, your point number, comma, 0 for removing the point from a group. If you want to add a point to this group, you would put 1. But in this case, we want to remove it if it is not the center point. So we're putting a 0, comma, and then set. And then you do a colon, and then you end your if statement. All right, so once that is done, you will see once again, the circle points group temporarily only has one point, and that is our center point for our geometry. Down below, we group promote circle points. We are going to promote the circle points group, that single point, into a primitive group, but we're going to keep the original group. And what will happen is if we go into primitive selection, you'll see what this does. It gets the primitives that point has on it. And you can see where this is going. We create a basic 4 primitive square from that center point that we just found. And we are going to expand that around the ring. And whenever it cannot make a full ring around this square, it stops. So in this case, we do not want include only elements contained in the original group. We do not want that selected. Otherwise, we will not have a square. See? So we need to turn that off. So we get a basic starting square. All right, so now we have a starting set of circle points group in points and circle points prim in primitives. Next, we are going to make another group node called process. Process is a temporary group, which we will delete later on. But what this does is you get a group node, you're going to make it a primitive group. The base group, we're going to put in the circle points prim, but we're going to put an exclamation point before it because we do want everything that is not the circle points prim group. So if you look into our viewport, you'll see that everything that is not in the circle points prim group is in the process group, and you can see where this is going. We are going to process each of these primitives and see if they can be added into the circle primitives node, if it's safe, if there is an edge loop that is perfectly around that square. And so we're going to process it one edge loop at a time, and pretty much this will be fed into the scary section, our while loop. So this loop right here, this is going to mathematically determine if an edge loop can be added to our circle primitives group. So if we go to the end of this node, you'll see what the final result is. The circle primitives group is a perfect square and thus can be turned into a perfect circle. Process group, all that's left to be processed is pretty much scrap that cannot be turned into a full edge loop. You'll see that there's holes everywhere. Where the process is, you cannot make an edge loop continuously with what's left. And so we will go over this for while loop bit by bit. And this is pretty much a basic for each loop that you've seen a billion times, but we are going to rig it so it's a while loop. All right, and what do I mean by a for while loop? You all know how for loops work, or for each loops. They go through each primitive or point, do a process. You know how by count works. It's a set number of times that you put here, but right now this is a little bit different. This is a for while loop. This will keep on going indefinitely until we reach a certain condition, which is put in here, which I'll explain shortly. What we are doing in this loop is we will be getting our circle prims group. We are finding the border points that are on the border of the circle points prim and the process groups. All right, and those are the border points. pretty much as we increase the circle primitives group, as each edge loop gets expanded by one square or one primitive, we are going to check each point on the border, and if any of those points on the border have under 4 primitives connected to it, the loop will stop. So that is what a do while loop is doing. It'll keep on doing that and expanding our circle primitives square to make a circle out of until it reaches a point on the border that has 3 or less primitives connected to it, such as so if it reaches this point right here, this only has 3 primitives, so it'll stop. And that is basically how we are doing edge loop detection. And how do you set up a for while loop? This is kind of a cheat, if you will, because there's no official for while loop. What you want to do is you just grab your normal for loop, hit tab, and so you can just grab any of these because you can change them later on. You lay down a for each loop. At the beginning right here, you are going to want to create a meta import node, which I've already done, and it's right here. All right, and right here you're going to put fetch feedback. This will allow it to access what each pass did. And at the end here, you're going to put by count, feedback each iteration. And then we have some vex code in here. All right, and by count, usually for a for loop, you can set a specific number of times to go through this. So how do you set it to an infinite amount of times and have it only trigger off during a stop condition? And that's what this is for. We have a detail attribute called count, which is set up right here. And I'll go through these in order one by one later on. But what pretty much the count detail is doing, it is grabbing the iteration number, which is right here. And the iteration number just pretty much keeps track of how many passes it goes through. And it starts at the number 0 for the first pass, number 1 for the second pass, and so on and so on. But in any event, the important thing to note is it starts at 0. We cannot have the count iterations amount start at 0 because then the for loop will not trigger at all. In our count detail, which is triggering how many times to go through this loop, we can ignore the yellow text. That's just for debugging. We are grabbing the detail iteration, which we input into the second input. Detail iteration, and we're adding 1. We have at least 1 pass to go through because, again, the iteration starts at 0. We need at least 1 pass, so we need to bring this up to the number 1. Otherwise, the for loop will not trigger at all. And we are incrementing this number 1 time for each pass, so that way it never reaches the final count in the iteration. So each iteration will be 1 number ahead of what the current iteration is. Long story short, it keeps getting iterated 1 by 1. This iteration number is always 1 ahead of the current iteration, so it never stops until we reach our stop condition. And what our stop condition is again, we are, as soon as it finds a point on the current edge loop that it's sorting through that has 3 or less primitives, we are creating a detail called stop, and we are making that it defaults to 0, and we are making that the number 1. And so that's what this is right here. This is what increases the count detail attribute. So as long as stop equals 0, that means it has not found a bad edge loop yet. So as long as there's a good edge loop, stop will be 0. So 1 minus 0 is 1. So we always increase the count detail to keep the iterations going 1 ahead of the previous pass. And once it reaches 1, and that means it found a bad edge loop and has to stop. So stop will equal 1, 1 minus 1. For the count attribute will equal 0. So the count attribute will just stop incrementing, and that acts as a safety to stop this from going. And then this will trigger as well the stop condition. So you need both, or actually you just need this, but as a safety condition, it'll stop increasing the iteration count. But the stop condition is as soon as this equals 1, it'll stop going. So if you read the helper text right here, if this parameter is 1 at the start of the iteration, looping stops. So if you ever want to do a for while loop, you just create a detail attribute, link it up in here, and whenever it reaches the number 1, it'll stop automatically. So you just need to make some math algorithm in Vex to have it equal 1, and you got a for while loop. All right, so we have this on single pass 0, so let's finally go through this one by one. Again, you make your iteration node by hitting this button, create meta import node. You're going to get your iteration node, and that'll keep track of how many passes. We put that into the second input of this attribute wrangle. Before we do that, the very first node we're going to put down is a group combine node. and we are creating the group add, and that is an edge group. That is how we're going to get our border points. We are pretty much saying when we're going to create an edge group, and it's going to equal wherever the circle points primitives, that is our square group, wherever that meets and intersects with the process group. So whenever these two groups intersect, that'll give us our border edge point, and then beneath that, we are going to convert that to a points group called add points. And you may say to yourself, oh, why can't you just make this a point group instead of an edge group? Because Houdini, for whatever reason, does not like that and will give you an error. So we have to go through the rigmarole of making this an edge group, then promoting the edge group to a point group called add points. And if we go into our viewer, you will see the add points are our border points for this very first pass. All right, so we have our group add points. And like I said before, we are going to go through each and every single point and make sure each point has at least 4 primitives on it. And if every point on the border has 4 primitives, we can go ahead with a second and third and fourth and so on iteration of the for while loop and keep on adding primitive squares to the border of our initial square and keep on growing the square to meet the size of the bounding box object. We do that by this attribute wrangle right here, which again has the original geometry in input 1, the iteration meta import node in the second input. All right, and what we're going to do is we're going to create these two variables right now. Int point count, ptct, equals the number of points coming into our original first input, and we -1, so because the points start counting at 0, and this is a detail attribute. We only want to do this once. Then you make a detail integer called I at stop 0. Make sure it's global so the final node at the end can access this. All right, now we're going to have a for loop with vex, and this is going to go through each single point one by one. We create an integer for int I equals 0. I has to be less than or equal to the point count, colons between all of these, and then end with I plus plus, and that'll increment. That is a syntax to increment the I integer for each pass of the for loop in vex. And then you put your brackets. Let me indent this so it's a little bit neater. All right, and then we're going to indent our brackets, and this is pretty much going to go through each point, and this is just increase the I check each point with that point number. So this is kind of acting like a point wrangle within a detail wrangle. So this is the syntax, if you're new to Houdini, of how to go about doing that if you ever needed to. You can see right now if in point group, and that is determining if a specific point, if point 0 is in this add points group, if point 2 is in this add group, and this again keeps incrementing. So if point I, whatever the current iteration is of this for each loop for the points, if that is in the group add points, we are going to get a point prims. You've seen prim points before, which I just showed. This is point prims. This is making an array of all the primitives that each point is connected to. So it'll say, oh, this point right here, return these 4 primitive numbers in an array. So that's what this is. This is an array of every primitive that is contained in the current point if it is located in our add points group on the border, because we don't want to process every single point. We only need to concern ourselves with the border points in the add points group. So, and then again, similar to how we did in the try trash node up above. All right, and similarly to how we did before, if this array is less than 4, that means so if any point has 3 or less primitives, we are going to set stop to equal 1, and break just breaks the loop, because we don't need to go through every other point if at least one of them has, as soon as it finds a point with only 3 primitives, we know that whole edge group in the add points group is dead and cannot be used, so we don't need to process the point, so the break will just immediately end the loop. All right, and once that for each loop ends, we are going to increment the count. So that's what I've talked about this before. So I at count equals detail, the iteration number, which is again fed through the second input, this node right here. We're adding 1 because this iteration starts at 0. We need this to start at 1. and this will increment. This will set the count number to the current iteration plus 1, and this will increment it to 1 beyond that. All right, so this makes sure our count number is always 1 ahead of the iteration, and this will keep on incrementing our count number as long as stop equals 0. But if this for loop catches a point on the add points group, that again will expand as the for while loop goes through. As soon as it finds a 3 primitive point, stop will equal 1, and then the at count detail will stop accruing, which will end the loop. All right, in case you're wondering, yes, we need both of these. It didn't work with only one, mainly because one, you can't have the iteration start at 0 because that means a for while loop won't trigger at all. If you have the for while loop at 1, it'll just stop at 1. So we need to make sure it's above 1 above the iteration count, and also that it keeps accruing. So, and then the stop condition and the iteration conditions are grabbing those two details that we created in this node above. So that is called attribute wrangle 7. If you go into the text, you'll see that is the syntax to get a detail. So detail, quotation marks, / forward. That means to look in this graph at this node. Attribute wrangle, get the string of the node. So / attribute wrangle 7, comma, count in quotation marks because it's a string. You get your detail for your count, and then comma 0, parentheses. And the 0 is just a default value in case there's an error. You always put that. That doesn't really mean anything. You're just always supposed to have that in the syntax. And likewise, we grab our stop condition. We grab our stop detail. All right, and beneath attribute wrangle 7, that checks each point, we have a switch node here. So what this is doing, and at stop condition, this is pretty much an algorithm. So 1 minus the stop number. This is input 0. This is input 1. If stop equals 0, 1 minus 0 equals 1, so it'll pick this side, and this pretty much keeps adding the primitives to the square as long as stop equals 0, so that means it can keep on continuing. We do not want to add the primitives to the circle prim group and increase the size of our square if there is, again, a bad point with 3 primitives and a broken edge loop. So if stop equals 1, 1 minus 1 will equal 0, and it'll pick this side, which does nothing, and the loop will immediately end. So this is not exposed. This is just a variable to determine which path we're choosing. So it'll pick path 0 if it finds a bad point, and it'll keep on picking this and adding those primitives to the group selection if the whole edge loop is good to go, and each point has 4 primitives on it. All right, so how do we add primitives to our edge loop? Coming out of the attribute wrangle 7, we will do a group promote. We're getting our add points group, which is our point group, and we are going to convert it to an add prims group. So let me see, the add points group, because we promoted it, is no longer available, but if we hit our primitives group and we take a look at the add prims group, you'll see that our square is now 1 edge loop bigger than it used to be. Circle prims 1, 4 squares. If I go to the group promote add points, you'll see the add prims is 1 bigger than the circle points prim, and we now need to add the add prims group to the circle points group, which we do down below. So we're getting a group node. We're calling it circle points prim, and there's going to be a conflict with the previous circle points prim group, so we're just going to say union with existing. And as a base group, you put in add prims, and so that'll just add the add prims with the circle points prim. And if we go into our viewer, you'll see that the circle prims group is now 1 edge loop bigger. But now if you look at the process node has an overlap. So we need to delete those newly added primitives on the edge loop from the process group so it does not process them again. So we pretty much say, create a new group node down here, and we're going to call it process, and we're going to replace the existing group process. And in the base group, we're going to put in exclamation point circle points prim. So it's going to take the process group and delete any primitive that is in the circle points prim, and we just added that edge loop in. So now if we look at the process node, it is 1 edge loop shorter than it used to be compared to the previous node. See? And now we've trimmed that off the process node. And now if we look at our circle points prim and our process group, on the next iteration, it'll check the border points on those newly expanded and contracted groups. So instead of getting the points for the add points group on the inner square. It's going to get them on the outer square now and keep on going and going until it hits one of these edges here. And for cleanliness sake, because we don't want to have the groups conflicting with one another for each iteration, we are going to delete the group add prims because that was only temporary. So, and we do not need to worry about it being deleted because it'll just get created once again on the future iterations. And that gets again fed into our switch node at the end, which gets fed into the final node of our for while loop. Okay, and sorry for the long-winded rant, but that finally ends our for while loop explanation. After the for while loop, we have some cleaning to do. We are going to delete the group process. We no longer need it. We are going to delete the attributes dist cent, which again measured the distance from the center point to each of the points on the add primitive to measure how far they are from the center. And we don't need that anymore. And we no longer need our count and stop detail attributes, so we're going to clean those up. Move on down to this node right here, attribute wrangle 6. And again, this has our original geometry, and we are going to copy over what we've learned from the for while loop with the deleted geometry onto the original geometry. And again, we are going to be using the ID attributes we used for the primitives and points to transfer everything over. So you're going to get I at pair prim, and we are going to find the corresponding primitives from the original geometry to the deleted geometry. And whenever their ID values match, we are going to transfer over the group that we just created, the circle points prim group. So that's what this is doing. So I at pair prim equals find attribute value, which I've talked about in my previous tutorial, but find attribute value will just look into the second input, which is input number 1 right here, and the first input is 0, obviously. Going to look into our deleted process geometry in input number 1, and it's going to look for a primitive attribute called prim ID. Whenever that matches a primitive in the original geometry, it's going to return the prim number of the deleted geometry because it doesn't match, and it's going to tell us what that number is in the matching geometry from the original geometry, and that'll be called the pair prim. So pair prim will return the new at prim num of the deleted geometry. So we know which primitive goes with the original geometry compared to the deleted geometry. All right, and we're going to create like a bool, a true or false, 0 or 1, int in group. And if the pair prim for each primitive, if it has a pair, is in the group circle points prim, it'll return a 1. If it's not, it'll return a 0. For each primitive in the original geometry, it's going to find a corresponding primitive in the deleted geometry. And if it returns a ID number that matches, we're going to check to see if that primitive is in the group circle points prim, which is going to create our circle, and return a 1 if the deleted geometry is in the circle points prim group. So those primitives that are highlighted will return a 1. If they are not, they will return a 0. And that'll lead us into our if statement. If at pair prim is greater than or equal to 0. Once again, if there is no matching primitive in the deleted geometry, because we deleted a bunch of them, it'll return a -1. So if pair prim is greater than or equal to 0, that means it found a match in the original geometry. If it's -1, that means there's no match, so it'll not process primitives that do not have a corresponding partner in the deleted geometry. If we go into our geometry spreadsheet and look at the I at pair prim, once again, you'll see -1 means there's no match. And if it goes all the way down, and these are the new primitive numbers that were assigned for the at pair prim. So as long as that is greater than 0, that means, or equal to 0, I should say, that means there is a matching primitive. So if that's true, and if it is in group equals 1, if that is true, that primitive is in the circle points prim group, we are going to set the primitive in the original geometry to the circle points prim group. So set prim group, parentheses 0 for the first input, the original geometry. We're going to put that into the string circle points prim in quotation marks, comma, at prim num, comma, 1 for true to add it to the group, comma, set. So pretty much it finds a matching primitive in the deleted geometry, checks to see if that primitive matching is in the circle points prim group, and then if both of those are true, it'll set the original group's geometry into the circle points prim group. As you've seen below, we now have our groups transferred from our deleted geometry to the full geometry. And down below, our circle points group needs to be updated. As you'll see, that is a mess because, again, bounding boxes only take points. You'll notice that all the points are here. That's because this is the original geometry. In the deleted geometry, it was one single point, but we are now working with the original geometry. So circle points are still every single point enclosed in the bounding box, so we need to fix that. We're going to delete the group circle points so it no longer exists, and we're just going to promote the primitive group circle points prim to the circle points. And we need that because those circle points are going to determine the shape of our circle. We will end that explanation with cleaning up and deleting a few attributes we no longer need. So we no longer need the point ID attribute. We are going to assign a new one later on. But first we need to clean this one because we are adding and deleting geometry left and right. So we need a fresh one. So we delete the ID group that we made. Later on we'll make a new one. And for the primitive attributes, we're deleting pair prim and prim ID. We no longer need them. And that finally gets fed into the second input of the use loop detection, which once again is exposed in the HDA. That is fed into the use bounding box option or use manually selected primitives for your circle shape, which again I've explained before. And that'll conclude the group section of the HDA. We will move on next to the circle math geometry, which, believe it or not, is much more simpler, and this graph gets more simple as it goes on. So oddly enough, just selecting the groups was the hard part. So should be smooth sailing explaining things from now on. So let's move on to how to make this into an actual circle next. Okay, everyone, thanks for watching. Once again, please visit gumroad.com/cinema for the HDA file for this. I also have a few other products on Gumroad. Houdini, the automatic hair card making kit for Houdini, as well as a course on rigging a game-friendly character for Unreal Engine using Houdini, as well as a few other products such as the pixel art substance designer filter that you can instantly make pixel art sprites out of for your 2D game or perhaps 3D game with 2D sprites. Also, I am on ArtStation at artstation.com/cinema, as well as obviously YouTube at youtube.com/cinema, and please subscribe. I am almost at 1,000 subscribers. I would like to push that to over 1,000, so I'm almost there. I'm on the doorstep. Thanks for watching. See you later.